So, if you remember, we have already discussed this trapezoidal rule to find the definite integral, like a definite integral, like a numerical approximation of a definite integral by using this trapezoidal rule. And if you remember its formula, the formula for trapezoidal rule is this one. A to b y dx. If we have divided this a to b interval into n subintervals, then this is the formula like h by 2 in bracket y naught plus yn plus 2 times of y1 plus y2 plus yn minus 1. And if you remember that how we drive this formula, what we did like in Newton Cotes formula, we have substituted n equal to 1, and first we have a given definite integral from a to b. We like write into sum of sub integration like x naught to x1, then x1 to x2, and then xn to xn minus 1 to xn. Here xn is b and x naught is a. And then we have applied our trapezoidal rule in each of these sub integration, and by taking n equal to 1 in our Newton Cotes formula, and finally we have this kind of I1. I1 equals to h by 2 I naught plus y1, I2 equals to h by 2 y1 plus y2, and like in the end yn equals to h by 2 yn minus 1 yn. And then because we are integrating this integration, so we added all these. So after adding, in the left hand side we have a 2by dx, and in the right hand side we have h by 2 y naught plus yn plus 2 y1 plus y2 yn minus 1. So this is the trapezoidal rule. And now we find the error we are getting in a trapezoidal rule if we are calculating this using our analytical method. And now we are calculating this using our, this part is like a numerical method. So this numerical value and this analytical value, what is the difference in the, or what is the error actually? So we'll establish one formula for error of trapezoidal method. So here, like we already know this, we have this integration and trapezoidal rule a to b y dx we have to calculate. So to calculate this y dx, uh, we subdivide the intervals integrals like this, and then each subintegral is approximated by this trapezoidal rule, and then we added all these subintegrals in value of subintegrals, and then we have mm, composite trapezoidal rule, and then this one is known as like a trapezoidal. So like we estimate. So here, if you see this, this is our I1 integration. Like here, I1 is given, and it is like x naught to x1 y dx. So if you like expand this y about this point x naught, now we are calculating analytically. Okay, no, we are not using any numerical here. We calculating this integral x naught to x1 y dx analytically. So what we do here, we expand this inside y by using Taylor's expansion. So we are writing the Taylor's expansion of the function. We are writing the Taylor's because this y is actually yx, and we are, if we are expanding it about the point x naught, so this is the Taylor series expansion. And like this you can infinitely contain all these terms. And so here we are actually writing its Taylor series expansion of yx. So here you can see that in the right side, like we have in left x naught to x1 y dx, and the y is now replaced by its corresponding Taylor series expansion. Obviously this yx naught in our notation is y naught, and other things are written as the terms of Taylor series expansion. Next, we integrate this using our analytical methods with respect to x. So if you integrate this with respect to x, so what we will get, like because here 1, so x, here you have x minus x naught as a factor, so its integration is x minus x naught whole square upon 2, and then x minus x naught whole cube upon 3, and 2 factorial is already there, and like this you will get. And then lower term, lower limit of the integration and the upper limit of the integration. The next job is the next job is to substitute x equals to x1 as an upper limit. If you substitute x equals to x1 in this, you will get this much expression, y x1, and this is x1 minus x naught square, x1 minus x naught, like this. And when you substitute x naught, x equals to x naught, you substitute, you will get 0 here, 0 here, only this term will remain, y naught x naught, other terms are 0. And if you club this term with this, then you have this as an expression. So you have obtained analytically this one. So this is like our what we say, we have calculated this analytically. Integration x naught to x1 y dx, analytically we are getting this. Now we know that in general, like we assume that this x1 minus x naught is h. So we have replaced this x1 minus x naught as h here. So this is like the value of the given integral from x naught to x1. Analytical value is given by this equation 1. Now we calculate what we are doing. We are approximating this by this formula. If you know the, like in each subinterval in trapezoidal, each subintegration in trapezoidal rule is approximated by this formula. So the approximated value is, because this is also equal to this one, and this is approximated value. So we'll calculate, we expand actually this one also by using Taylor series expansion. And then we'll say that the Taylor series of this approximation and Taylor series of this up to how, which power of h they are matching. So we'll see, like h by 2 y naught plus y of x1. Obviously y1 is your y of x1. This already know that this kind of notation we are using in numerical method. And then y naught yx1, then y naught as it is. X1, obviously you can write x naught plus h, so you have replaced here. And then you have kept your h by 2 outside, this y naught as it is, and here in this part only you have expanded again this by using Taylor series expansion. Like there is another form of no ya plus h. Hello. Okay. So y of a plus h, if you remember, then it's Taylor series expansion, like ya plus h y dash a plus h square upon 2 factorial y double dash a, like this. So we have expanded this y x naught plus h by again Taylor series expansion. We are getting this kind of expression. And then next we multiplied this h by 2, and finally we have this one. So we are having here approximated values is given by this, and the exact value is given by equation 2. So if we minus equation 1 from equation 2, I will get the error in the first first sub integral. Like this is the first integration, so I will get the error in the first sub integral. So error in this I1, like here E1 is representing, like you can say, error in I1. So if I subtract 1 minus 2, I will get the error, because 1 we are getting through exact integration, and second we are getting through it's what is the value of its a numerical approximation. And then we will see after this is exact and this is approximate, and we have both expanded in terms of Taylor's series. And then we see that if I minus 1 minus 2, then hy naught will cancel out hy naught. So this will cancel out this, and this will cancel out this, but this will not cancel. Like h cube upon 4 and h cube upon 3 factorial y double dash of x naught. So this term will not cancel, and further terms also. So these two terms cancel, so we have substituted 0, and then 3 factorial is 6, so 1 by 6 here, and 4 is already here, so 1 by 4. H cube and y double dash of x naught you have taken out, and the other powers, like because here h raised to power 4 terms also, h raised to power 5 terms also, we have represented like order of h raised to power 4, whatever we are getting after subtractions. And then if I simplify it, the simplification I will get this one, minus 1 upon 12 h cube y double dash of x naught plus order of h raised to power 4 terms. So this is the error in the integration I1. But I have like I2 also, because when we develop this method, we have this I2, and this is like in. So I have to add all these error, because when I am integrating a to b fx dx, I am adding all the numerical approximation of all these sub integrations. So I have to add error also for all these sub integration. Then I will get the error in the this integration a to b y dx. So as we did for the integration I1 from x naught to x1 y dx, we again perform the same operation and we'll get this error e2. The point x naught is replaced by x1 here, because now the lower limit in I2 lower limit is x1 to x2 y dx. So now you expand, if you are interested in repeating the process, so you have to expand y about the point x1, and then you have to do all the calculation we have did for this I1, and then in the end you have this change, you will find y of x1, and other things are remain the same. And similarly for en also, minus 1 by 12 h raised to power 3 and y double dash of x and minus 1, because you know that in in the lower limit is this. So now if I add all these error e1 e2 en, I will get the error in this. So the total error in the numerical approximation of this integration by using our trapezoidal rule is the error, like a sum of all these e1 e2 en. So you can see 1 by minus 1 by 12 is common to all terms, h cube is also common to all terms, and the other things are as we have written, y double dash of x naught, y double dash of x1, and y double dash of xn minus 1 plus order of h raised to power 4 terms. Again, I assume that because like I am expecting what is the maximum error can it be. So what I assume, like there are y double dash of x naught, there are y double dash of x1, y double dash of xn minus 1, but any one of them is the maximum of all remaining values. So I suppose like if it is maximum for like xi, so I say like x bar is my xi, and now y double dash of xi is greater than in terms of absolute sense actually it is greater than y double dash of xi when I is ranging from 0 to n minus 1. So it means there's for x bar in particular I'm saying it is like xi, but it is greater than like xi is greater than for all. And even though like instead of writing the same notation, if I change the notation, then it will be like for all j, and j is ranging from 0 to n minus 1. So if I am assuming that this is the maximum error in any subinterval interval and integral, and which is greater than the all of other y double dash of xi. So what I did like minus 1 upon 12 h cube is there, and then I replaced them by the maximum error like this, like like this I have to write. So like maximum error, absolute of y double dash of x bar. X bar is nothing, one of the x naught or x1 for which y of xi is greater than the other remaining y double dash of xi. And then this is like h cube. I know how can I write or choose n in trapezoidal. I choose n by like b minus a upon h. So I substituted the value, and y double dash of x bar is there. And then like this is the final error. So the error in like a generalized trapezoidal or composite trapezoidal rule is minus h square upon 12 b minus a y double dash of x bar. So what it says actually, y double dash of x bar is there, and h square is there. So it says like if you integrate a to b y dx using your trapezoidal rule, it will give exact solution. It means the error is zero if y is a like a constant, or y is like a 1 degree polynomial, because here the second degree of or second derivative of y is involved. So it means that if y is actually constant and you differentiate it two times, so obviously you will get zero, and in this case also y double dash is zero. So if y double dash is zero, so error is automatically zero. So it means your trapezoidal rule uh, give exact value if your function y is either one well, degree polynomial or a constant polynomial. For more than 1 degree polynomial for x square, it is not going to give you the exact value. It means there is an error, and error is given by this expression. So this is the way we proved the error of trapezoidal rule. So in the similar way, like you have to prove for Simpson one third formula, and like you add this question in your assignment, that you have to find the error in a similar way using Simpson one third formula. Now we'll discuss some problem like this theorem we have already proved. I think this one is also visible to you. So if fx have two continuous derivatives on this interval a to b, then the generalized trapezoidal formula having error this h square h square upon 12 b minus a upon 12 f double dash of cn. Here it is cn. We have taken x bar. Am I audible?
Yes,
Hello?
sir. Yes, sir.
Okay, okay. Actually, the internet disconnection, I don't know why. So I will continue in this thing in the next class. So today I stop here because through mobile I cannot do this thing. And one more thing, like, can you tell me when up to like because right now I know that there is no internet and like for 5 minutes I am talking continuously and without internet. Can you tell me up to what where we have discussed in this? Anyone?
Sir, you have just started the PDF of trapezoidal correction.
PDF of
Error, sir. Error in trapezoidal rule, sir.
error in trapezoidal rule.
Yes, sir. New PDF. I think 26 pages or 28-page PDF. That one.
Okay, okay, okay. That you have not listened anything about
Yes.
this.
Yes, sir.
Okay, then I will continue. And actually, I have continuously speaking for last 5 minutes, and I don't know this. If this is the situation, na, like internet disconnect is, you just call me, okay? Otherwise, like that, if I don't see, then I again talking. No one is listening up around 10-15 minutes. No,
Okay, sir.
okay, you just call me in next time, na. These are your internet having problem. Check it. Okay. Okay, now I am leaving. I will give attendance to all of you. So the class test is on November 2. I think 10 to 11 is the time.